And we're back again. Now we're going to look at a couple more proofs, so we're going to get some more experience having a go at proving things before we introduce a bit more logic and a few more proof techniques. Okay, so these are just some more examples of things, so more examples. So let's look at a divisibility example. And again, we aren't desperate to prove lots of divisibility results in this course, but it's a good place to start because the amount of mathematical sophistication we need isn't very much, and so we can really concentrate on actual details of proving stuff rather than getting into the nitty-gritty of, oh, how on earth do I do X, Y, Z? No, we can concentrate on the logical structure of the proof without getting bogged down in too many technical details. Okay, so let's look at our result here. The result is just if A divides B and B divides C, then A divides C. And so, as we will with almost all of our proofs, we're going to start with scratch work and by assuming the hypothesis is true. Because we know from the truth table if the hypothesis is false, nothing to do. So the only time we have work to do is when the hypothesis is true, and we can ignore the case that the hypothesis is false. So almost all of our proofs will start with this. Okay, so scratch work and hypothesis is true. So we start off by assuming that A divides B and B divides C. And then we make good use of our memorized definition of divisibility to know that, by the definition of divisibility, this tells me that B is some multiple of A, so B is equal to K times A, and C is a multiple of B, so C is some other number, L times B, where K and L are integers. Now we want to show, and this is also a good thing to do here, so we've just fleshed out what does the hypothesis mean, but it's also a good idea to look at the conclusion. This is part of our scratch work, part of experimenting and playing with the problem. It's a good idea for us to work out what does the conclusion mean. Well, A divides C means that A is a divisor of C, so C is a multiple of A, where n here is just some integer. Okay, so this is our conclusion, and this is our hypothesis. So all we're doing is trying to understand what does that mean, what can we deduce from the hypothesis, what do we need to show for the conclusion. So we're just playing with the problem a little bit. Okay, well, since C is a multiple of B and B is a multiple of A, well, we can just put these together, substitute in B, which we know from here, into that expression there to get C is a product LKA. Well, since K and L are integers, we know that K times L is an integer. That was one of our axioms back at the start. So KL is an integer. And we're done. We've shown that C is some integer times A. Now, of course, we've worked out how to do the proof. What we need to do next is take this scratch work and write it up nice and cleanly, neatly, none of this scribbles and so forth, so that it's easy for the reader to understand what's happening. Now again, remember the reader isn't necessarily an actual person here. This is just a good device for us to think about how do we write down the proof. We should imagine that someone is going to read our work, and we should think about what do they need to know, what don't they need to know, how can I explain that nicely for someone, and so forth. Okay? So not necessarily a real person, but often it will be. Often it will be the person who's marking your homework and your exams. You want to make it easy for them to understand what you're doing. So we need to clean up our scratch work. We need to clean up all of this rough experimenting work that we've done. We need to make sure that the logic flows correctly. So in the correct direction, we haven't started from the conclusion and reached the hypothesis. We've started from the hypothesis and gone to the conclusion. There's no dead ends. We don't scribble anything out. We keep the presentation neat and tidy. And we're presenting this work to the reader. It shouldn't be a mess. It should be clean and coherent and easy for them to understand. So one thing we can do to aid that is we can skip what might be very obvious steps, like expanding a polynomial. But we should only do that if they're very obvious to the reader, not to you. So you remember, you've been in there working on this problem, you understand the problem, you've been playing around with it. The reader might not have been. So you should only skip steps when they're obvious to the reader, not necessarily to you. Okay, so you have to think about, what does someone who is coming to this problem afresh, what do they know, what don't they know? Okay, so be careful skipping steps. Make sure the text is very easy to read. We add these little phrases like hence, we know that it follows that, just so that the text flows nicely, so that as someone reads it along, there's these little helping little nuts of sentences that make it comfortable to read. Now, dot point, so putting dot, a sentence, and so forth. That's okay when you're learning how to write proofs, but we should do away with that eventually. Similarly, when we write this little triple dots, meaning therefore, don't write triple dot, write therefore. This is okay in your scratch work, but it shouldn't happen when you're actually writing up the proof. Use words. Words are good for you. They won't hurt you. Okay? So let's see what our proof looks like now. So our proof, we're going to start by assuming the hypothesis is true. We're just telling the reader that. Later on, we might start to skip that step, but we'll probably always put in something like, oh, okay, assume blah. So we'll tell the reader where we're starting from. Okay, so we'll almost always have a sentence that looks a lot like this. So now we assume that A divides B and B divides C. That was our hypothesis. And then we expand that out to say, oh, by divisibility, it means that B is K times A, C is L times B, for K and L in Z. Now notice I haven't written by the definition of divisibility. I'm going to assume the reader knows that. I'm going to skip what I think is probably pretty obvious, that my readers understand the definition of divisibility. But if in doubt, I should put in a couple more words. Okay? So I'm going to assume A divides B, B divides C. So I know that B is K times A, C is L times B. Well, it follows almost immediately that C is K times L times A. And since K times L is an integer, we know that A divides C as required. So I've started from the hypothesis and reached the conclusion. Now, to make sure the reader knows this is the proof, all of it, I'm going to start by putting proof up at the top. I've put everything here on this slide in a nice box, but when I write this on a page, if I was writing by hand, or if I was writing this in a document, not on a slide, then I'd probably put proof at the start, and at the end I would put this little square. This is a very standard bit of mathematical notation, meaning, hey, that's the end of the proof. Okay, let's do another one. So let's do an inequality now. So let x and y be real numbers, then x squared plus y squared is always bigger than or equal to 2 times x times y. Now, inequalities tend to be a little bit difficult, and they tend to be difficult to prove, so let's mess around with the scratch work here. Now, inside this result, the statement of this result, there's really an implication hiding here. It's really telling me that if x and y are real numbers, then this inequality holds. And in this course, we haven't really done very much about inequalities. The only thing we've really stated about inequalities was this fact that the square of a real number is not negative. And so what we want to do is try to make this inequality look like a square, because that's really the only thing we know stuff about so far. So let's rearrange the inequality to make it look like a square. So if I pull this 2xy over to the other side, I can write it as x squared plus y squared minus 2xy is bigger than or equal to 0. And I can recognize this as just the square of x minus y. And this is what we want. The square of something is non-negative. But let's be careful here. The order of logic that we've just used is kind of backwards. I know this fact, and I want to prove this fact. But in my working here, I've started from essentially what I want to prove, though I've just boxed that very badly. I've started from what I want to prove and reached something that I know to be true. So it's kind of backwards. So let's be careful with that. So it's very important when we do write up our proof that we verify that in our scratch work, our logical flow is good, okay, that it's going in the right direction from the hypothesis down to the conclusion, not the other way around. And in inequality proofs, it's pretty common when we're just manipulating the inequality that we'll actually start from the conclusion, the thing that we want to prove, and manipulate it around to get back to something we know to be true. And that's exactly what just happened. We started from the conclusion and we manipulated it around to make it look like something we know to be true. Okay, well, we can still salvage something here, and this will actually turn out to be okay. So let's just see what we've got written in this proof. So assume that x and y are real numbers. Well, we know as a fact that the square of any real is non-negative, so we know x minus y squared is bigger than or equal to 0. So I've just sort of started the proof, kicking it off from this line. And as the reader, that might be a bit mysterious. Why did they do that? But in the proof, we don't have to explain why, we just have to show that it works. So the square is non-negative, so we know this thing here. By expanding that out, we get to this expression here, x squared minus 2xy plus y squared is 0. And so by pulling this term over to this side, we get the required inequality. And so again, if I was writing this on paper, I'd write proof at the top, and at the bottom here, I'd write little square. Okay, so be careful with inequality proofs. Very often, the flow of the logic in our scratch work is backwards from what we actually need.